This is a recorded webinar about recommendations for advancing best practices for the preservation of nutrient samples. There were two analytical teams involved, my group from Plymouth Marine Laboratory and Stefano Cosi from the National Research Council, CNR, in Trieste, Italy. The scope was that the aim was to compare two of the most widely used methods of long-term nutrient sample storage, which were freezing and pasteurization, and to recommend on best practice for sample storage in the future. Pilot activity involved two partners from the EuroGO-SHIP consortium and took advantage of planned cruise programs in different regions of the European seas, which were the English Channel, East and North Atlantic, and the Mediterranean. Specific objects and goals were to describe the rationale, methodology, and data sources for the nutrient sample storage experiments, to present a summary of the results for the preservation activity, to identify and discuss the lessons learned and best practices from the experiments, and to provide recommendations and suggestions for the future. Let's first review the background and methodological history to nutrient sample storage. There are a very broad range of methods that have been reported in the literature over past decades, and scientists have struggled to find what they think is the best way of preserving nutrients when it is not possible to analyse them at sea. Freezing at -20 is most commonly used as it is simple and non-invasive to the samples. However, you do need a freezer, obviously, and of course this will need mains power supply, which is not always readily available. But then sample shipment can often be a difficulty, and you're actually in the hands of shipping companies, and you never really know if your sample has not been defrosted in its journey back, quite often from distant oceans where the research ships come in. Pasteurization, involving heating samples to 80 degrees for 2 hours and then cooling and storing in the dark. This means the samples can then be shipped along with all the other equipment in a shipping container, and it needs no specific conditions to bring them back to your own laboratory. However, this does require a good accurate oven, and it is quite important that these ovens heat properly all around the unit. Another method used is poisoning with the addition of mercuric chloride. It's reported as a good method in the literature, but here obviously there are problems with user handling of the mercuric chloride, which is a poison, a marine pollutant, and then you have to handle the waste. And then basically every single sample is a waste because it has got mercuric chloride in it. So potentially we're looking at a lot of waste. Also, the mercury will affect the reduction efficiency of the analytical nitrate column. And so, in some cases with a lot of samples, this could mean a loss of a column. Chloroform and other compounds have been reported and again have shown some positive results. But again, here we have a toxic and hazardous substances that are to human health. And again, you're adding something to the seawater sample, and our opinion is that ideally you should add nothing. And you've got acidification with hydrochloric acid, but then samples must be neutralised before analysis by the sodium hydroxide to bring the pH back. So again, you've got the addition of material to the sample twice and the risk of contamination. And the acid can potentially cause the hydrolysis of organic phosphate compounds. Alkalization with sodium hydroxide, basically the opposite of using HCl. So in this one, the samples have to be neutralised with HCl before acid. So again, the same issues as just mentioned. So the main two that tend to be used by people around the world are freezing and pasteurization. So we chose these for the pilot study as they are the most commonly used by the community. So the sampling activity for the team from Trieste, working in the Gulf of Trieste, you can see that they collected samples in May 2023 from 6 stations in the Gulf, and you can see the water depth is quite often between 10, 15 and 20 metres, with a deeper area to the south of the Gulf. But this is a very shallow lagoon. They use small boats. Obviously, you couldn't get a proper research ship in there, and so this made the restrictions as to why they couldn't actually analyse on board these vessels. The samples were collected at the surface and bottom using horizontal 5-litre Niskins, and then stored in 5-litre HDPE tanks on the small boats. The tanks were kept refrigerated and in the dark, and then taken back to the CNR lab for processing. Sampling stations are located around there, and each of these is affected by various atmospheric forcings, circulation of water, and by runoff from the rivers, both north, Isozono, and the Rizzana, for example, in the south. So once the samples were taken back to the laboratory, the analysis started. The time zero was about 1 month after the sampling occurred in the Gulf, and then further samples were analysed at 6 months and at 12 months. You can see the results on the right-hand side, where there is a lot of variation between the different samples. The nutrient concentrations do not stay constant over the year for either both frozen and pasteurized. So the frozen samples are in the blue, and pasteurized in the red, and filtered are the open circles. So you can see there's quite a big disparity between particularly nitrite, where the filtered are in many cases higher, but again the between sample replicates is very poor. Syringe filtration of the samples with the 0.22 pore size filters maybe was causing possible release of nitrate and ammonia due to the breakage of the plankton cells. And then there's possible overestimation of phosphate in the non-filtered samples due to the dissolution of the natural particulate phosphorus. In non-filtered samples, the pasteurization can increase the concentrations of phosphate and silicate because of remineralization of both particulate and dissolved organic phosphorus and biogenic silica. In the filtered samples, generally pasteurization increases the concentration of phosphate with respect to the frozen samples, again possibly due to the remineralization. But overall the results weren't clear from this coastal area. The second sampling program was carried out on board the RRS James Cook, and with one station in the Western Channel and then the others in the East and North Atlantic. You can see there the sampling site for the station L4, as it is known, which is part of the Western Channel Observatory, which is just off Plymouth. That was the first station that was sampled on this cruise. And then we moved out to the PAP site, the Porcupine Abyssal Plain, which again is a long-term sampling site where they do various measurements and have static buoys there for the rest of the year. And at this site we took varying depths, and so hence with varying nutrient concentrations, to look at the effects of the pasteurization and the preservation on samples with varying nutrients. So for now we're looking at the sampling and the analysis of the nutrient samples. So from the first station, which was L4 in the Western Channel, we deployed a 24 Niskin bottle CTD rosette with 20-litre bottles. It was a full water column analysis, and 3 CTD bottles were reserved for the EuroGO-SHIP sampling. The ATSI analysis was carried out with a 5-channel SEAL analytical AA3 colorimetric segmented flow autoanalyzer. And this was for nitrite, ammonium, silicate and phosphate. You can see here the analyzer at sea, and also there the standard CTD being deployed over the side of the ship. Samples were also taken for analysis during the sampling of the CTD bottles to check on the homogeneity of the 20-litre bottles and that we weren't getting any layering, which would skew the results. Clean sampling handle techniques were employed, acid wash bottles, nutrient-free vinyl gloves, etc. And the sampling is according to the Go-SHIP nutrient manual. So for each actual sample, triplicate bottles were taken for each one, and then they were randomly packaged. Acid cleaned 60ml HDPE, which is high-density polyethylene bottles, were used for the sample freezing and pasteurization for the nitrate, ammonium, silicate and phosphate. And we also used, as recommended by Danielle et al., 100ml glass shot bottles, which they were used for pasteurization for the ammonia only. Sufficient samples were taken for up to 15 months of future analysis, but in fact we actually continued the analysis for 12 months. 45 HDPE bottles were sampled for both freezing and pasteurization, plus 45 glass bottles for pasteurization only at every station. You can see the HTP bottles that were randomly labelled, put together for future analysis. The oven with its full of the samples ready to be pasteurised, and then the oven itself. It's actually very important that before you do the experiment that the oven is tested and checked, and you work out how long it takes for the samples to actually heat up to the 80 degrees. So this must be taken into account before you actually start your 2 hours of pasteurisation. And also you need to check that your oven is a suitable fan oven that can distribute the heating capacity right through the oven and not to have any cold spots which would affect your pasteurisation. As I say, the method of pasteurisation is as described by Danielle et al. 2012, which is 80 degrees for 2 hours. So something else we need to check is the homogeneity of the water in the CTD bottles themselves. So to ensure that these aren't layering and you're getting a uniform nutrient concentration throughout the bottle. So these were taken in these 20-litre bottles, which can be up to 1.5 meters high. And we see the results here, and these are different subsample bottles, just taken from the different CTDs at different depths down the bottle. So you can see for each of these there is very small variation, a standard deviation from the concentrations of each of these bottles. So we were quite happy that these bottles remained homogeneous whilst they were being sampled, and this sampling quite often took 45 minutes to an hour for all these bottles to be sampled. So here we're looking at the experimental outline for the coastal and offshore samples. In the Gulf of Trieste, you see here on the left, it was a coastal site. It was not possible here to do the near real time because these were sampled in small boats and there are no facilities on board. So the real time was in fact samples that were analysed about a month after the samples were returned to the laboratory. Also here, because of the nature of the water column, you would ideally filter these samples because of the nutrient, the particulate loading. So for them here, they had the non-filtered long-term storage and the filtered, and then freezing and pasteurisation. So for the coastal water off Trieste, there was a lot more samples to be taken and obviously analysed in the future. On board the RS James Cook, it was a lot simpler. The real-time analysis was carried out on board, and that was carried out in less than an hour after the samples returned to the deck in the CTD. Then they had the long-term storage. These samples were not filtered. The water column, surface water column, was oligotrophic. There was almost no phytoplankton in the water column. And standard practice is not to filter. Filtering, again, however clean you make it, there still introduces the possibility of some contamination. So we did not filter any of the samples from these offshore samples for the Plymouth work. We should now look at the various water samples that were taken on the RS James Cook cruise. And this is the one that was on the English Channel and at the Porcupine Abyssal Plain. So the aim was to sample different water masses with contrasting nutrient concentrations. And you can see from the diagram here, EG1, which was the L4 site, the depth of 50 metres, low nitrate 0.25, nitrite approaching detection limit, silicate low, and phosphate 0.16. Then at the Porcupine Abyssal Plain site, we have three different sampling stations. EG2, which is at 200 metres, we had nitrate of 8 and phosphate 0.46. EG4, which is 500 metres, the nitrate obviously is increased down the water column, 13 and phosphate 0.78. And then one at the bottom, EG3 at 4,824 metres with 22.7 nitrate, very low nitrite, undetectable ammonium, silicate of 46.8 and 1.5 for phosphate. So this gave us a very good cross-section of nutrient concentrations for comparisons for the two preservation methods. When we finished the freezing, when we came to do the analysis, just to say that the The frozen samples were defrosted according to the nutrient manual, EuroGO-SHIP nutrient manual, which is 45 minutes at 50 degrees, and that's in a water bath, and then 45 minutes at room temperature. And this is from Becker et al. 2020. And alongside every run, carried out an analysis of an Atlantic water CRM, and this was to ensure the analytical data quality and comparisons between each of the analytical runs. So looking now at some of the results from the Plymouth sampling program, as you can see at the bottom is weeks from time zero. Time zero in this case was actually the samples taken and analysed fresh on the research ship. So it gives us the true zero. The other samples were then either frozen or pasteurised, as we've just seen, and then taken carefully back to Plymouth, and then kept ready to be analysed over the time series for the next year. So we look at nitrate. This is for EG3, which is the 4,824 metre station, the deep one. If you look at nitrate and nitrite over the year, pasteurised, it's a very small drop, but it's less than 2% a loss and less than 1% overall for the frozen. For phosphate, the pasteurised, again, there's a slight increase, but again, it's probably within the sample variation. That's less than 1%. For freezing, there is an overall drop of about 7% for the frozen samples. So again, at EG3, we can again see for the silicate, there was a very slight loss down, but we're talking very high concentrations here, relatively high concentrations for silicate. And so you can see the drop is less than 1% over the 52 weeks for both pasteurisation and the frozen samples. Nitrite, it's quite a lot of variability. However, both of these started at about 0.025, 0.03 micromolar, which is heading towards the detection limit of the method. So I think this is probably one of the reasons we are seeing, because the scale is enlarged, that the changes in the error bars are looking quite large. But however, you can see there's a drop down to below detection limit by about 20 odd weeks. So the nitrite is didn't preserve well by either method. So now we move on to station EG2, which is at 200 meters. You can see again from the phosphate and the pasteurised over there with the 52 weeks. The frozen phosphate loses more of the concentration over that time, although percentage-wise it is only about 2 to 3%. Pasteurised hardly drops at all, but again it can be seen, same as EG3, that pasteurisation is better for the phosphate. For the nitrate and nitrite, the frozen, again, very small increases, but still quite a bit of variation in the samples, and almost none in the pasteurised. So obviously no changes, no significant changes within the analytical uncertainty, and just really showing up there was variations between the duplicate samples. So also for the EG2 station at 200 meters, if we look at the silicate for frozen and pasteurised over the 52 weeks, very, very small overall increase for the frozen samples, but not really significant at all. And likewise, pasteurised, again, rises very small, but really small increases. Nitrite, again, as seen at the deep station, again, it was very low concentrations, just above the detection limit. And you can see that for both pasteurised and frozen, the concentrations drop off over the year, and again down to becoming below the detection limit for some of the samples. So again, nitrite is not seen to preserve very well for both methods. So now looking at the results for the EG4 station, which is at 500 meters depth, where the phosphate was about 0.78 at the start of the year, and nitrite was about 13.2. So over the course of the year for the phosphate, for the frozen samples, it's just a very small increase, just between about 2%, 2 to 3%. But for the pasteurisation, it's quite a large drop, down to about 0.725, and a big lot of variation, inter-sample variation. For the nitrate, Again, and for both that and the pasteurised results, you can see both of them over the course of the year lost concentration. Losses weren't high percentage-wise, but there was big variation between the various duplicates. The other two nutrients now for the EG4 station, it's the silicate and the nitrite. Silicate started off at about 5.6, went down to about 5.45 by the end of the year for the frozen samples, and actually almost exactly the same decrease for the pasteurization. I would say both of those are within an accepted uncertainty of 2 to 3%. The nitrite, again, has been seen with the other samples, has not preserved well, either using frozen or pasteurization. But again, the initial concentration was low at about 0.02, and then drops off again for a great part of the year to below detection limit. We were looking at ammonium specifically. There's been, over the years, most people, I think, accept that ammonium is, if not impossible, but very difficult to preserve, and should really always be analysed at sea. So looking here at the results for the 12 months, this is the EG2 station. It started off below detection limit, and then over the course of the year, there was a general trend upwards, with actually percentage-wise a large increase from the initial below detection limit concentration. Frozen showed not as high an increase, but again an increase over the year, and again a great variability between sample sets. Then for the ammonium for the glass, which was specified specifically by Danielle et al. As being better than freezing, you can see that actually again it still shows an upward trend, and overall for this experiment appears to be the worst. So again, looking at ammonia, and this is from the EG4 station. Again, it started off below detection limit, but then over the course of the year, the results again are fairly just, well, there's no pattern at all. There is an increase generally over the course of the year, but again showing that in the case of this experiment, preservation is not recommended for ammonia. Generally, for phosphate and nitrate, for non-filtered open ocean samples, losses are within a 3% error, which may be considered acceptable. A greater overall percentage change in error the lower the initial concentrations has been seen from our results. And silicate preserved well by both techniques for loss or gain within 2 to 3%. Nitrite, there's a loss trend for both, with big variations and in duplicates, but initial concentrations were close to detection limits in most cases. Ammonium storage for all situations shows an increase in concentration trend for all samples, poor duplication, but most initial concentrations again were at or below the detection limit. And glass vials are preferred to HDPE using pasteurization. The presence of particulates or biological material showed the efficiency of preservation varies among the different nutrients, and syringe filtration can cause breakdown of the plankton cells and release nutrients. And so low pressure should be used if samples are being filtered. Enhanced phosphate in non-filtered samples suggests dissolution of natural phosphate particulates, which increase the concentration, and maybe due to the high temperature and low pH in the analytical analysis method. Filtration using low pressure should always be carried out in sampling of coastal waters where there's particulates in the water column. However, pasteurization appears to increase the phosphate where the organic P is high in respect to the inorganic P. So this technique should ideally be avoided where organic P is high. In non-filtered, there's some evidence that pasteurization increases silicate and phosphate concentrations because of dissolution and remineralization of biogenic silica and or dissolved organic P. Pasteurization is ideally carried out on filtered samples. Reproducibility of methods of determination varies inversely with the concentrations. The breakers of plankton cells during filtration and dissolution of suspended organic matter decrease the analytical precision. So now we're going to start looking at some of the conclusions, including recommended considerations for best practice. The current best practice documentation for nutrient analysis and sampling and analytical methodology considerations is found in the EuroGO-SHIP Nutrient Manual, which is Becker et al. 2020. This, however, only discusses nutrient sample preservation and refers to various published methods, but does not make any recommendations for best practice. So the two most commonly used methods were therefore used for this EuroGO-SHIP nutrient experiment, so as to be able to be better advise the European nutrient community as the best way forward. When deciding between the two techniques, then, in many ways, the availability of a freezer or a relatively large volume oven for sample heating should obviously be considered. And probably because most labs have readily available freezers, then freezing is normally favoured as the best and simplest technique, involving little sample manipulation, and why it's a generally favoured method for sample preservation. Again, if you can sample at sea, then that is the best practice. A pasteurisation oven must be of suitable size, must be fan operated, and must ensure heating to all parts of the oven to the required 80 degrees C. And this needs to be checked before being used on samples. And also the heating of the samples and how long it takes them to get to temperature before you then start the 2 hours of pasteurisation. Considerations of sample shipping also need to be considered, and if long distances are involved from distant oceans, then it may well be advantageous to sample using pasteurisation, and so those samples are just brought back normally without frozen samples and having to ship across time zones for a number of days in transit. So the final overall conclusion for advancing the best practices for preserving nutrient samples is, wherever possible, analyse the nutrients. This should be carried out at sea or in the field using fresh samples analysed as soon as possible after collection. Especially true where nutrient concentrations are depleted and down towards detection limits. The long-term results of using freezing and pasteurisation are seen to be variable, and not one technique of preservation is seen to be superior to the other. So generally, decisions about the method chosen will therefore be an individual laboratory's choice. It will also depend on the reliability of returning frozen samples from the sample location, which may well on a research ship docking in a foreign port. Pasteurised samples can conveniently be returned, as we have seen, along with the rest of the scientific equipment once they've been preserved.